Thank you, Ramin. Hi, everyone. My name is Nivedita Mahesh, and I'm a postdoc currently at Caltech. And today I'm going to be talking about the imaging performance of FARSIDE in a big picture case. And I will talk briefly about how I've used the same pipeline to assess the modeling systematics, array systematics on OVRO, which serves as a ground pathfinder for FARSIDE array. So quickly, what is FARSIDE? FARSIDE is a NASA-funded probe-class mission to place a low-frequency radio array on the far side of the moon. When I say low frequency, we are aiming to cover frequency between 100 kilohertz and 40 megahertz, with the aim to actually study two main science cases. One is studying the dark ages and cosmic dawn. This is through the 21 centimeter redshifted 21 centimeter line from neutral hydrogen. So this redshifted 21 centimeter line from corresponding to dark ages, the hydrogen in the dark ages is expected to fall at frequencies below 40 megahertz. Hence, we need low frequency arrays, and hence we are going to the moon. The second science case is studying the magnetospheres and space environments of habitable planets. So we have seen and observed radio emissions corresponding to the magnetosphere of planets in our solar system. And we know from observations that most of these radio emissions due to the magnetospheres of exoplanets actually occur at frequencies lower than 10 megahertz. And models predict that we should expect similar things for possible hot Jupiters orbiting known M dwarfs. So with these two main reasons, we are looking to design this array to observe at really low frequencies, and we are going to take advantage of the Artemis mission and piggyback on one of those missions. Okay, so what is the planned FARSIDE mission architecture? This is what it looks like. So we'll have a base lander from the CLIPS mission, the Commercial Lunar Payload Services, and it'll have the base station. The base station will have the high gain antenna that will be used for communication. And then we'll also have 4 solar panels. And now the most important thing is we'll have 4 robotic rovers that will deploy the elements of our array. Now, each rover will have tethers, like I've indicated, tethers here embedded in them, tethers like rolled up. So as the rovers go out, they will lay out the tethers. In the tethers are embedded the antenna elements or the array sensing elements. And that's the plan we have for it. So speaking of the array, what is the array layout that we have planned for? For the science cases, the optimal array layout that we have planned is this 4-arm spiral configuration. This is an array layout, a bird's eye view of the array layout. The center is the central base station. And as you can see, there's 4 tiny rovers laying out the tethers that contain the antennas. Now, again, a few parameters. The number of antennas that we are envisioning is about 128 pairs of antennas, frequency range of 100 kilohertz to 40 megahertz. Each of these antennas will be 100-meter dipoles. Since they're so long and for convenience of deployment, we have decided to embed the antenna in the tether. So a few things to note that are essential at this point. So as the rover rolls out these tethers, it will place one antenna. Let's call it the X dipole as shown here. This is the tether, X dipole. And then the rover will turn 90 degrees and place the Y dipole. And this will create one pair or one antenna node. I'm stressing on this because we want both the dipoles so that we can make some dual polarization measurements that is essential for both the science cases. But I'm also stressing because this is unconventional. We do not, in most of the radio arrays, when we have the 2 polarizations, we have the 2 polarization face-centered. But just because to take advantage of the deployment strategies using rovers, now you see there will be a phase offset between the 2 dipoles, 2 polarization dipoles. And this will lead to a few concerns and performance that has to be looked into, which is where my work comes into place. Now, so the dipoles that will be offset will lead to polarization leakage. Now, why are we so concerned? Because one of the science cases that I mentioned is to study the exoplanet atmospheres. The radio emissions from the exoplanet magnetosphere is produced by a mechanism called electron cyclotron maser, and it actually that mechanism produces highly circular polarized data. And it helps separate the host signal, the star signal from the planet, because the star is also expected to produce radio bursts. So it's essential to have good polarization data so that we can tell what signal is from the planet. Now, if we have polarization leakage, this can cause confusion in the Stokes circular polarization data that we get. So in general, in radio arrays, instrumental effects, your beam, I will show you your beam itself will cause source polarization mixing, but this additional antenna offset causes more polarization leakage, which is where I carried out a work to understand the leakage, model it, and maximize the performance of FARSIDE. Okay, to get into some plots. So the first thing I did was I took the dipole pair X and Y, and I simulated it on regolith. Okay, so now the X and Y, I'm keeping it face centered. I'm not adding the offset that we expect. I keep them orthogonal in the same face center. I place them on regolith and look at its beam and see how much polarization leakage can we expect, which is what I'm showing you on the right. These are Muller matrices plots to quantify how much polarization leakage we can expect. The first column actually refers to how much Stokes I of the sky goes into the instrument Stokes I, Q, U, V. The second one is how much the Stokes U of the sky goes into instruments Q, I, Q, U, V, similarly U and V. So in an ideal case, all we want is only the diagonal terms. That is, Stokes I of the sky should be picked up into Stokes I of the instrument, Q into Q, U into U, and V into V. But we do see non-zero terms in the off-diagonal matrices, but they're small. Now, this happens because of the beam. Because of the dipole beam, you will see polarization leakage. Now, what if we take the second case that FARSIDE deployment strategy will have? That is, the two dipoles will have an offset. It is expected to have a 50-meter offset. And in that case, I'm going to go back and forth between these slides again. See the last two rows. The leakages in the last two rows gets worse when you have an offset between the dipoles. And the last row, if I may, is actually the Stokes V that we are capturing. And like I said, we want high fidelity Stokes V data so that we can study our exoplanets. And the other thing that I want to note that here I'm plotting this for one frequency. And as the frequency changes, these leakages also change. So these plots, I'm trying to highlight that, yes, the beam itself causes some polarization leakage and mixing. Offset adds to it, and it's important to model it and correct for it when we get our images. So for that, I developed a custom pipeline that will process these beams from FARSIDE and get us take the sky model, process through the FARSIDE pipeline, and see the dirty images we get. So in this pipeline, the input model I gave is a sky model from Gleam catalog, and it only has Stokes I. I process through the pipeline and go through the FARSIDE beam and the UV layout, and this is what I get as the output. The first one is no offset. So I get the Stokes I back, but I also get some Stokes V, non-zero. And when I take the 50-meter offset, the Stokes V increases by 3 orders of magnitude. Now, all's well, where we do have a correction. If we know the offset between the dipoles exactly, we can get back the Stokes V to be down to what you expect for the no offset case. So we do have the pipeline in place. We have a correction in place. But the main caveat here is that given we know the offset between the dipoles exactly, and all the offset between each of the dipoles are at 50 meters as expected. So the main thing, we're almost at the end. So the main thing I wanted to say that this pipeline will inform the deployment strategy team that up to what levels of errors in terms of placement of the offset or the angles between the dipoles we can calculate, we can tolerate. So I'm just going to leave my discussion up, and also for further discussion, I have extended the pipeline to OVRO, the telescope in Bishop, but we can leave that to discussion later. But I just wanted to say the deployment strategy will have an offset between the dipoles that will affect the imaging performance, but we have a pipeline built to correct for it, given we know the deployment positions of the dipoles well enough. Thank you.